This is the video on Newton's third law. So just to review a couple things, inertia, that is the property of all material bodies to resist a change in their motion. So that is Newton's first law of motion. It's known as the law of inertia, and you've probably heard this before. Objects at rest remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. And Newton's second law is known as the real law of motion. So it's usually just written as the equation right here. The acceleration equals the net force divided by the mass. Newton's first law of motion, he stated that net forces cause acceleration. Newton's second law of motion, Newton quantifies how much acceleration is produced by any given net force. And the amount of acceleration, as you can see, is produced depends upon the ratio of net force to the mass. So now in Newton's third law, Newton states, well, I know what causes that acceleration, the net force, but where do those forces come from? So if we look at a tug of war demo, this one you can try at home if you have spring scales. But the first volunteer will have an easy job, while the second volunteer will have the harder job. One of them just pulls and the other holds it still. Then you sort of switch. The other pulls up to like 10 newtons, the other does not. You'll be able to see that this is not possible. Even if you're just holding that spring scale, you won't be able to get it to, I can't pull without the other person pulling. And that brings us to Newton's third law of motion. It is known as the law of action and reaction. So you've probably heard this one before. For every action, there's an equal and opposite reaction. And you can see it is written right here. You can write it mathematically. The force that A applies to B is in the opposite direction, but equal to the force that B applies to A. Now, there are 5 key components to Newton's third law that aren't explicitly stated in the law. So forces always occur in pairs. There's no such thing as a lone force. Force pairs are always equal in magnitude. Force pairs are always oppositely directed. Force pairs always occur simultaneously. So what that means is that they start at the same time, they end at the same time, they're applied for the same amount of time. Now, force pairs never cancel because they act on 2 different bodies. So let's just look at this horse cart riddle. So there's a famous physics problem known as the horse cart problem. It goes something like this. A farmer wants to take his produce to market, so he loads up his cart and tells his horse to giddy up. The horse turns and looks at him and says, "No, it would be futile for me to pull on the wagon because by Newton's third law, if I pull on the wagon will pull back on me with an equal and opposite force. As a consequence, there will be no net force and thus no acceleration. Therefore, I will just stay here grazing on the grass." Well, what the horse said made sense to the farmer, yet the farmer knows that horses routinely pull carts. So what could the farmer say to the horse to convince the horse that he could accelerate the cart? Explain the proper application of Newton's third law to this problem, and I give you a little hint here. Are the force pairs acting on the same object? These force pairs are acting on 2 separate objects. With the friction of the horse pushing on the ground will accelerate the car forward. So essentially what this means is that, look, the horse is going to pull on the cart. Well, by Newton's third law, there's an opposite and equal reaction. The cart pulls on the horse. These are opposite and equal. But if we look at the free body diagram of each, if we look at the cart has a very low frictional force because it is on like wheels. You can see that there's an applied force. Well, now if we look at the free body diagram for the horse, well, the horse isn't on wheels, so it's going to have that frictional force. Now, if we look at the applied forces, these are my force pairs. Notice that one of them is acting on the horse, one of them is acting on the cart. They are opposite and equal, but what happens is that that frictional force that the horse is pushing with is going to accelerate that cart forward. So there will be a net force and it will accelerate, right? So it has to do with that friction. It's not really the applied force. So if we look at something like this, which football player is hitting harder? Well, you'd probably be tempted to look at this and say, well, it's the person that's hitting the one with the helmet coming off. So let's just take a look at football hits, right? So let's take a look at 2 different players. I just label them A and B, which either exerts a larger force and magnitude on the other player. Well, by Newton's third law, we know that those forces are opposite and equal. Which player applies the force first? Well, they're going to be the same. Force pairs are simultaneous. They start at the same time. Which player applies the force for a longer period of time? Well, force pairs are simultaneous, which means that they're applied for the same amount of time. Now, if the forces are equal and opposite, why don't they cancel out? They're being applied to two different objects. One's being applied to player A, one's being applied to player B. Which player does that force have a larger effect on? So you can just look at this and say, okay, the effect is going to be larger on player A because, well, his helmet's coming off and he's falling down. These players are hitting each other with the same force and magnitude. However, the effect of those forces are not the same of each player. Now, there is another concept called momentum that we'll get to later that does come into play with this. But like, just look at B on A on B, but the effect is going to be different. So let's look at an easier one to sort of conceptualize here, right? Let's look at a bug hitting a windshield. So which object, the bug or the windshield, exerts a larger force and magnitude on the other object? They're going to be the same. Those force pairs are going to be opposite and equal. Which object applied that force first? They're going to be the same, right? Force pairs are simultaneous. Which applied the force for a longer period of time? They're going to be the same. Now, if the forces are equal and opposite, why don't they cancel out? Well, the answer is because they apply on two different objects. One's being applied to the windshield, one's being applied to the bug. Which object, the bug or the windshield, does that force have a larger effect on, right? It's going to be the bug. It's going to have a larger effect on the bug. The forces that are applied to the bug and windshield are equal. However, the effect of the bug is much more noticeable, and you can see that in the splat. So here I've got the bug on the windshield on the bug. If we look at like the free body diagram, it's sort of hard to tell there, but notice that the windshield is connected to the car. It has a much larger mass. So that effect isn't going, which means it resists change in motion more. So that little bit of a force isn't going to have much of an effect on that large car, but it's going to have a large effect on that bug. It's going to accelerate a lot more. So to demonstrate this, we did this lab. It's called Don't Nickel and Dime Me. So in this lab, so you slide a nickel and a dime in the diagram. There it's a penny. Doesn't matter. You just have one large, one small coin. I used a dime because a dime is the smallest coin. So during the collision, which object applied the force first? Well, it's going to be the same, right? The nickel and the dime apply the force at the same time. During the collision, which object applied the force for a longer period of time? They're going to be the same. During the collision, which object did that force have a larger effect on? So they're opposite. They're equal. They're applied for the same amount of time. They start at the same time, end at the same amount of time. But it's going to have a larger effect on the dime, that smaller coin, because it has a smaller mass. Which had a larger acceleration? Well, it's going to be the dime, right? Because the ratio of net force to mass is going to be different. So if I look at the Newton's second law here, the net force is going to be the same on both coins, but because the dime has a much smaller mass, it's going to have a larger ratio of net force to mass, thus a larger acceleration. You can see here the free body diagrams for the nickel and the dime or a penny. So let's just answer these questions. What do you think would happen if this lab were to be conducted again, but with a quarter instead of a nickel? So essentially what you're doing is you're adding more mass. So the force when they collide, that's going to be the same on both objects, but it's going to have even less of effect on the quarter because it has a much larger mass than the nickel. What do you think would happen if we were to be conducted again, but two of the same coins? The effect is going to be the same because of Newton's second law, because the net force on these coins are going to be the same. The mass is going to be the same. So the ratio of net force to mass is going to be the same. It's going to be the same effect, same acceleration. Explain why the penny or the dime, whatever being used, and the nickel accelerated the way they did during the collision. So essentially what this is, we've sort of already answered this, and it's because, well, the smaller coin, the dime or the penny, has a much lower mass. It resists that change in motion more, so it's going to have a larger acceleration, a larger effect than that larger coin, because the larger coin has much larger inertia, much more mass, thus it resists that force more than the smaller coin. So now let's answer this question. How do rockets work in the vacuum of space where there is nothing to push off of? So in order to answer this, we did the HERO's engine. So if we look at the HERO's engine, all we did was we poured water into the HERO's engine up to the designated line. So in the past, I've done like, hey, 250 milliliters. It doesn't really matter. We're just going to continually pour more more liquid into the Hero's engine and watch it spin. Make sure the straws are bent to match the diagram off to the right, and let it spin. Count the number of spins, then manipulate the red line on the graph to represent how the amount of water affects the number of times the Hero's engine spins. So you could get an exact number, but I mean, you do get an exact number when you fill it up to these certain lines. But what I wanted you to see is that the water amount as the water amount increases, the number of times the Hero's engine spin increases as well. So let's just answer these. While the Hero's engine is spinning, which object, the water pushing on the straws or the straws pushing on the water, exerts a larger force and magnitude on the other object? So it's going to be the same force and magnitude, because force pairs are always equal in magnitude. Now, while the Hero's engine is spinning, which object, the water or the Hero's engine, applies the force first? They're going to be the same. Force pairs are simultaneous. Same thing, same answer with this question. Which object applied the force for a longer period of time? It's going to be the same because they are simultaneous. Force pairs are simultaneous. They're applied for the same amount of time. So what I had you do was I had you do two different diagrams. Right? These are sort of like free body diagrams. The Hero's engine with the straws bent. Use the red arrows to represent the forces acting on the Hero's engine by the water. Use the green arrows to represent the forces acting on the water applied by the Hero's engine. So what I wanted you to do is there's two here, one where the straws are bent, which the Hero's engine spin, one where they aren't bent, where they did not spin. Look at the diagrams above. Would the Hero's engine spin if the straws were pointed straight out on opposite ends? Well, the answer is no, and here's why. It's because of the red arrows. The red arrows are what's acting on the Hero's engine. When the straws are bent, you'll notice that there's like this torquing motion, right? I've got one arrow, one of these red arrows like pushing on the Hero's engine down, one of them pushing up. You've got like a torquing motion which causes it to spin. When the straws aren't bent and they're straight out, these red arrows sort of balance each other out. These aren't opposite and equal, but what you did was when you made the straws straight, you made the forces acting on the Hero's engine balance out. So let's just answer some of these questions. What happened to the number of times the Hero's engine spun as the amount of water increased? Explain why you think this is. Well, the forces might not be might be the same in all of these cases, but when you put more water in the Hero's engine, the water comes out for a longer period of time, the more water. So you're applying that force for a longer period of time. So that's why it spins more, because it's spinning for a longer period of time. So in the future, I might have somebody time it just to see the time. Use Newton's laws to explain why the Hero's engine spins. So because the straw is bent and it's pushing the water out. It's redirecting that water. It's pushing the water out. The water is also pushing on the straw, the Hero's engine. Now, because they're bent, it creates that torquing motion. The force being applied to the Hero's engine is sort of off-center, creates that torquing motion, and it spins. But it's because of Newton's third law. That's why the water just doesn't fall out and it doesn't spin. It's because of Newton's third law. The straw redirecting the water is being pushed out of the straw, while the water is pushing right back on the Hero's engine. So let's answer this question with the next slide. But cars accelerate by using the friction of the ground. Airplanes fly by pushing off the air in Earth's atmosphere. Space is a vacuum, which means there is nothing to push off of. Use Newton's third law to explain how rockets are able to accelerate in the vacuum of space. So let's take a look at how a car accelerates. The tires are rotating but not sliding on the ground. The tires are providing a frictional force on the ground. The ground is providing a reaction force on the tires. Now, planes act the same way except with air resistance. The engine, those turbines are pushing the air back. The air is providing a reaction force on the engine, pushing the plane forward. So let's take a look at how rockets accelerate in space. So space is a vacuum, which means there is nothing to push off of. So how do rockets work in space? So in order to answer this, let's just look at the diagram here, right? So I've got a car, it's a mass. Tires are pushing on the ground's pushing on the tire. That net force, that reaction force, the ground on the tires is what causes that net force and causes it to accelerate, the car to accelerate. A plane works the same way. The engine pushes on the air pushes on the engine, and then there's that air pushing on the engine pushes the plane forward, that is what's going to cause that net force, causing that airplane to accelerate. Now, rockets ignite the fuel by pushing gas out of the back at incredible speeds. The ignited gas is providing a reaction force on the rocket. So what happens here is that, well, rockets push the gas out of the nozzle in the back. The gas pushes on the rocket, and there is a net force. So rockets have to bring something to push off of in space. You have to have that reaction mass. If you don't, like, there's no friction, right? Just like a car uses. There's no air, just like a plane uses. All rockets have to bring what they are going to push off of with them, right, as fuel, and it just ignites that gas, launches the gas out of the nozzle. That reaction force accelerates that rocket. So what happens to you if you get separated from a spaceship? So if we look at this, if you get separated from a spaceship and you don't have your rocket or whatever, just doesn't, you're out of fuel or something, if the astronaut has something to throw, like a wrench, there is hope. The astronaut should throw the object in the opposite direction of the spaceship. So if we look at the wrench and the astronaut exerts a larger force and magnitude, they're going to be equal. They both apply the force at the same time because they're simultaneous for the same amount of time. Force pairs are simultaneous. If the forces are equal and opposite, why don't they cancel out? It's because they're acting on two different objects. One's acting on the astronaut, one's acting on the wrench. But it's going to have a larger effect on that wrench because it has a smaller mass, but it does have an effect on that astronaut, right? So throwing anything in the opposite direction will accelerate the astronaut in the direction of the spaceship. So what happens is I've got the astronaut throwing the wrench on the astronaut. I do have a net force. And as long as you can go past zero and go the opposite direction, you will slowly be able to get back to the spacecraft, right? So that wrench is going to fly, but it's going to be a small acceleration. And as long as you have enough acceleration to go the opposite direction, go back towards the ship, you should be able to make it back, right? So these are the free body diagrams. There is a net force acting on the astronaut as they are throwing that wrench. Here's another question. What determines the winner of a game of tug of war? So this one's kind of a tricky one. So I've got Team A and Team B. Which team exerts a larger force and magnitude by pulling on the rope? It's going to be the same, opposite and equal reaction. Which team applied the force first? Going to be at the same time. Force pairs are simultaneous. Which team applied the force for a longer period of time? Well, it's going to be the same. The force pairs are simultaneous. So how does a team win a game of tug of war? Now, I'll give you a hint. What is applying a force in the outward direction? Would it help or hurt a team if they were standing on ice during a match? So if we look at this, A is pulling on B, B is pulling on A. The go-to is, well, obviously it's the team that's going to pull harder, the stronger team. That's not true, because just take a look at this. These forces are going to be the same no matter how strong the other team are. But let's just say I put Team A on a block of ice and Team A on like a rubber mat. Well, you can automatically say Team B is going to win. Now, to summarize this, a team wins a game of tug of war by applying a larger frictional force than the other team. Now, since friction is affected by the nature and condition of surfaces and how hard those surfaces are pressed together, the team that is heavier and can get a better grip on the ground will usually win. That's what the technique is for. The technique is to maximize that frictional force in the opposite direction. Now, there are other factors that go into winning a game of tug of war, but pulling harder won't be the deciding factor. It usually has to do with the heavier team because they're usually going to have a better grip, right? So you can see here, it's the team that's going to have the larger frictional force. Obviously, if I put a team on a brick of ice and another on a rubber mat, well, the one with the ice isn't going to have a larger friction, causing it to accelerate in that direction. So that's how you win. You win by getting the best traction. So why was tug of war removed from the Olympics? So this was a tug of war controversy, right? In the modern Olympics, the tug of war contest was between two teams of 8. One team had to pull the other 6 feet along in order to win. If after 5 minutes no team had done this, the team which had pulled the greatest distance was declared the winner. Now, these are the winners in 1908. Great Britain, and you can see your City of London Police, Liverpool Police, Metropolitan Police. Now, what do you notice about all these winners? They're police, right? Now, at London in 1908, the American team protested its first round loss to the Liverpool Police, claiming that the Liverpool Liverpoolians were wearing illegal boots. When the Liverpool team challenged the United States to a rematch without shoes, there was no response from the Americans, who withdrew their team comprised of athletes competing in other events. So here's the rules that were stipulated in the rule book for tug of war. The rules had stipulated ordinary shoes. And the police teams, they just said, well, their giant work boots were ordinary to them. So they were able to use their giant work boots. Now, work boots are designed for traction. So when playing tug of war, the team that had the best traction will usually win. Technique does play a role, but when they were playing in the dirt, the police with the large work boots were able to get a better grip. And then I think in the next, after 1912, it was removed from the Olympics. So here's another Newton's third law riddle, right? Can you figure out the birds on a truck? A man is delivering a huge flock of birds to an aviary. They are all sitting on perches inside a truck, but the truck comes to a very steep hill and it cannot get up because the weight of all the birds. So the man gets out, bangs hard on the side of the truck, putting all the birds into flight. He then hops back into the cab and is able to drive up the hill. Now, would this work? So the answer is no, this does not work, right? And it's because like the truck is like a sealed container. When the birds fly, they're pushing that air down. Well, the air is in turn pushing on the ground. So it doesn't negate that weight. That weight is still going to be in there because the birds are pushing the air in a downward direction. How much does the earth weigh? Well, remember weight versus mass, right? So mass does not depend on location, closely related to inertia. It's only a magnitude, which makes it a scalar quantity. Now, weight, remember, it can change with location. It's closely related to gravity. So let's just take a look at Earth's weight, right? So Earth is pulling on that person. In fact, it's pulling on everything around us, holding it to the ground. Well, the person is pulling back on the earth. Well, remember, weight is just defined as the gravitational pull, the force of the gravitational pull on that object. So if I ask the weight of a person, like, great, everything we say relative to weight is going to be the weight of that object on Earth because Earth is pulling all these objects down. But if I said, how much does Earth weigh? That doesn't make much sense because let's just say I weigh, I don't know, 800 newtons. Earth is pulling on me with 600 newtons of force. I'm pulling on the Earth with 800 newtons of force, right? 800. Relative to me, the Earth is going to weigh the same amount because the gravitational pull is the same. That's why when we talk about like planets, we talk about the mass of the planet. How much stuff is that planet made out of? It doesn't make much sense to say how much does a planet weigh because if I said relative to me, the Earth would weigh the exact same amount as me if I'm using myself as that reference point for the Earth. All right. Can you move the Earth using nothing more than a penny? So this one's kind of a cool little trick. Which object, the Earth or the penny, exerts a larger force and magnitude? Well, we know Newton's third law says that they are equal, right? Equal in magnitude. They're simultaneous. They apply the force at the same time, begin at the same time. They're opposite and equal. They don't cancel out because one force is acting on the penny, one force is acting on the Earth. But obviously that force is going to have a larger effect on the penny because it has a much smaller mass. So let's just take a look at this. Earth has a much larger mass than a penny. The Earth is pulling on the penny. The penny is pulling on the Earth. It's the same magnitude of force, but I've got a net force acting on both the penny and the Earth. Well, I've got a large acceleration, but notice that, yeah, there's a small net force acting on the Earth. It's still not zero. It's not zero. So, yeah, using Newton's second law, the penny accelerates toward the Earth at negative 10 meters per second squared, but the Earth accelerates up towards the penny at this amount, right? So it's a non-zero number, and it's not really pulling the whole Earth upward. It's more of like, it'd be more of like a stretching motion a little bit, but it does have an effect. It has to have an effect because of Newton's third law. Could you prepare yourself for blowing on your own sails? So this one's kind of tricky. I put this one at the end because it is sort of a tricky question. So the air is going to push on the fan, right? The fan pushes on the air pushes the fan. So this is how a normal boat, like an airboat, works. But if I have a sail, the air is going to push on the sails push on the air. These are the forces that are acting on the boat, and they should cancel out. So if you watch some videos that try this just on a smaller scale, it does not work. Now, this one gets kind of tricky because, like, if you look at this photo when the Mythbusters did it, they actually showed that you could, and it does have something to do, I think, with the sails being curved. I've watched many explainer videos on this, like read articles on this. It is kind of a tricky topic. Like if you just look at it, theoretically it shouldn't work, but there is more at play here. So you could look at it and it would work. It would work, like if the sails are curved in the right condition. I always put this one because this one still confounds me, right? Even though I've been teaching physics for a long time, it still confounds me, and I really like it when I run into problems like this. So as a final thought, remember there's just too much unknown in the universe to take a break from learning. Get out there and question everything.